Okay, welcome back Physics 20s to our next lesson. This is 1.5, we're looking at kinematic equations, and this is part 1. In the previous lesson, we looked at acceleration. So if we had a question like this, where a 2016 Chevrolet Camaro SS goes from 0 to 100 kilometers per hour in 3.9 seconds, we were able to calculate the acceleration, and we were able to calculate the instantaneous velocity at a certain time, for example, 2 seconds. But now we're going to look at how do you calculate how far down the track it's going to hit that 100 kilometers per hour. And to solve for questions like this, we're going to use kinematic equations. Now, the first one we've actually already been introduced to. It was A is equal to VF minus VI over T. You don't always have to write that triangle, but it does mean change in time. And this equation is the one that we used from the previous lesson, but it's also known as the first kinematic equation. We have already been introduced to that, so today we just have to introduce to one more, which is going to allow us to solve this problem here. But instead of just providing the formula, I'm going to show how it's built from other formulas that we have, so you understand this isn't just made up out of nowhere. So it says how far down the track, so the displacement from when it started to when it finishes at 100 kilometers per hour, what's this displacement when it reaches that speed? Well, before, the only formula we had that dealt with displacement was velocity is equal to displacement over time. If we were going to solve for displacement, we would rearrange with velocity times time is equal to displacement. But the problem that we run into is what velocity do we use? If we have a vehicle that goes from 0 kilometers per hour to 100 kilometers per hour, it changes from 0 all the way up to 100 kilometers per hour for its velocity over that displacement. So which velocity should we choose? Well, like I mentioned in the last video, for this course, we're going to assume that all accelerations are occurring at a constant rate. So its rate of speeding up is staying the same. And if that was the case, halfway down the track, it would hit 50 kilometers per hour, and it would be traveling less than 50 kilometers per hour exactly half the time, and more than it exactly half the time, and the average would be 50 kilometers per hour. And then we'd be able to use that average to calculate how far it has gone, given that the second time that it's going faster and the amount that it's going faster is the same amount of the time that it was going slower by the same amount that it was going slower. So basically the velocity that we're going to use is velocity average. Okay, so how would we calculate the average? Well, again, if it's a uniform rate of acceleration, velocity average would be equal to your starting velocity plus your finishing velocity divided by 2. So I'm going to say VI plus VF divided by 2. So now what I'm going to do is I'm going to combine these two equations by writing VAV in for that velocity. So I'm going to start by writing that our displacement here is equal to our velocity average multiplied by the time. Now the equation for velocity average was here, and it's VI plus VF over 2 times time, and that is going to be our new kinematic equation. It's written a little bit differently, but this is what's on your formula sheet. It is the same equation. It says displacement is equal to half of VI plus VF multiplied by T, and this is kinematic equation number 2. There are 4 overall, and in this lesson we're looking at the first 2. Again, the first one was the same that we used for acceleration, and this is the second equation. Now for solving kinematic equations, this process is what I'd like you to use because it's an easy way to determine what formula you're going to use and what to rearrange for. So there are 5 variables. There is VI, VF, acceleration, time, and displacement. To solve a kinematic equation, list all of these 5 variables and then determine what you have, what you don't know, and what you need. And then the variable that you don't know and the one that you're not trying to solve for is the one that you don't want in your equation. So if this was your sheet of paper over on the side, you just write down all 5 of those variables like this, and say you know VF is 10 meters per second, VI is 0, the acceleration is 9.81, but you don't know the displacement or the time. This is really common. You're only going to know 3 things. You're going to have 2 unknowns. If the question was asking for displacement, you'd say, okay, I know these. I'm going to want those to be in the equation, and I'm solving for this. So I need that in the equation, but I don't need time. So then you'd be looking for the equation that doesn't have time. Similarly, if you were asked for the amount of time and you had all this information, then the displacement isn't important. You're not solving for it and you don't know it. So you'd look for the equation that does not have displacement. And once we get all 4 kinematic equations, there will be one that has all of those except displacement, and you'll be able to pick the right one for each of those scenarios. But anyway, let's solve this one. I was talking about the Camaro going from 0 to 100 in 3.9 seconds. So I already found which formula I'm going to use because we kind of built that equation. It was displacement is equal to half VF plus VI If you put VI plus VF, I think that's how I actually showed it before, they're being added together. So the order of those two don't matter, times by time. I'm solving for displacement, so I'm just gonna put D is equal to half. And now I have to put VF in. And it's important to note that it says kilometers per hour here, but gives me a time in seconds. I do need the units for time to be the same. I would prefer this to be in meters per second because that's probably the most common one that we're going to see. So I need to turn that 100 kilometers per hour into meters per second. I mentioned in the last video, all you have to do is divide by 3.6. You'll get your answer in meters per second from kilometers per hour. And we get a number of 27.7 repeating meters per second. So I'm going to put that in here, 27.7 meters per second. Plus VI, it starts at 0 kilometers per hour, but that's 0 meters per second as well. And I multiply by the time, which is 3.9 seconds. We have the units matching up. Now I just need to plug into the calculator. I'm getting a number of 27.083 meters. And I'm gonna round my displacement to 27 meters then, because there was 2 digits in the question. You may be wondering, well, what about the 0? That was only 1 digit. I guess I could have put 0.0 there, but meaning from stopped. And stopped is like 0.000 going on forever. So don't really look at zeros for considering significant digits. Now I want you to try 2 questions here with the video and calculate them after I read it out. So it says that a car is moving at 105 kilometers per hour in the east direction. The driver sees a deer on the road 30 meters in front of it, east, so in front of it where the car is going. And the driver slams on the brakes and comes to a stop in a pretty impressive 3 seconds. Does the driver hit the deer? So I want you to pause the video here, try the calculation, and then play when you're ready. Okay, so let's check to see how you did. First step that I did was list out the variables right here. I know my VI is 105 kilometers per hour. I know my VF is 0. I know my time is 3.0 seconds, but I don't know the acceleration or the displacement, okay? So I know the time is 3 seconds. I'm trying to figure out where we end up as a displacement after that 3 seconds. I don't have the acceleration, but I'm not trying to solve for it. So that's kind of the useless variable in this case. We want the equation with VI, VF, T, and D. And that's the one that we have over here that we introduced in this lesson. I do want to note that I converted to meters per second because we had seconds for our time. So that's 29.16. I have D is equal to half VF plus VI times T. Then I plug in for that and I get a value of 43.75 meters. So unfortunately, he does hit the deer, which is not good. You don't want to be hitting deers, but I think in physics, it's sometimes good to consider how these equations can affect our lives and maybe how you could prevent hitting the deer. So let's go back to the equation and look at how we can decrease this number for a displacement, maybe so it'd be under 30. You see we have VI plus VF divided by T. This number of VI plus VF we want to be lower. So how we could do that is we need to come to 0. We can't really change the VF, but you can change the VI. If you were driving at a slower speed, then you would be able to stop with a sort of displacement from when you began to stop. So lowering our initial speed could make it safer for avoiding things like a deer. The other thing would be to decrease the amount of time. Well, how do you do that? The only thing that we could really consider here was if it takes you a certain amount of time to brake, part of that is going to be the time that you need to notice the danger and then react to start braking. We don't really know what that 3 seconds was composed of, and 3 seconds is pretty fast. But how you would reduce your time from going quickly to stop would be you begin braking as soon as possible. And the thing that can sometimes increase your time is if you become distracted by something, or you could become fatigued. So if you're driving too late at night and you're really tired, if you're impaired by any alcohol or drugs, or if you are on your phone or something like that, that's going to increase the amount of time it's going to take for you to brake because there's a reaction period. So to be driving slower and to be focused, and of course not under the influence of any drugs or alcohol, that's going to help your time or your reaction time to be as fast as possible, giving you the best chance to stop as short as possible. So I think it's good to consider how these things affect motion and the physics in our lives. The next one says, beginning at rest, a drag car completes a quarter mile, which is about 402 meters in 11.4 seconds. That's quite a fast time. If the acceleration is constant, what is the velocity when the car completes the quarter mile? Again, I'd like you to try this and then check back in. Okay, so let's take a look at how you did. First step, you list all the variables, VI, VF, AT, and D. We know our velocity initial to be 0. We don't know our velocity final. We don't know the acceleration. We know the time is 11.4, and we know the displacement to be 402 meters. So acceleration we don't have and we're not looking for, so that one gets crossed out. We need VI, VF, T, and D, and it's the same formula that we used before. It won't always be this formula. Once we have all the equations, you're going to see that you have to pick between those four. But for right now, we're using that equation again. But in this case, we don't have to solve for displacement. We already know that. We're trying to solve for VF. So the rearrangement here was I got rid of the half by timesing by 2, and then I got rid of the T by dividing by T, and then got rid of the VI by subtracting VI. And I have a formula here, 2D divided by T minus VI is VF. I put 2 times 402 meters divided by 11.4 seconds, and we get 70.526 meters per second. When I look in the equation, in this case, we have 3 digits here, 3 digits here. So we put 3 digits in our answer, which is 70.5 meters per second. Now to convert this to kilometers per hour, if you're interested for how fast that was, now instead of dividing by 3.6, we times by 3.6, and you get actually a pretty fast number. It's 253.89 meters per second. Again, to 3 digits, that'd be kilometers per hour, which is really quite quick. However, I do want to put a disclaimer in here that this is not completely accurate, because when a car is going to be speeding up from like 0 to 100, it's not going to be accelerating at the same rate the entire time. We're making that simplification for all of our questions because it would involve some fairly complicated physics to not assume that. But that's not often what happens when a car is going to be accelerating. It'll have a really high acceleration probably initially, but then less so when it gets up to a higher speed. So that's probably not quite accurate to what its actual speed would be there, but it gives us still a rough estimate and shows how we could use this calculation for constant accelerations. That's it for today's video. Make sure you ask any questions you have in the live time, and I will see you in the next video.